My name is John Mallinckrodt. I am your host for Bite of Physics. I'm a retired professor of physics who loves introducing lay people to the amazing view of nature that is only, and the universe that's really only available through physics, in my humble opinion. So that's what we do here every week, and we talk about well-established physics, usually with a little wrinkle or two, like we did last week. I introduced a real wrinkle, which is associated with the fact that I really am trying to avoid the A word in my Newtonian mechanics. And that's not asshole, that's acceleration. I'm trying to kind of stay away from the word acceleration. So we're going to do a little recap of what we did last week, and then we're going to use it in the context of a cute little brain teaser about buoyancy. I want to talk about buoyancy. That's a good topic in Newtonian mechanics itself. It's also about a different kind of a force, if you want. And it's always it's easy to construct brain teasers having to do with buoyancy. So we're gonna use this brain teaser and look at it in several different ways to kind of see the utility of the approach to statics that we talked about in the first few episodes of the Newtonian mechanics series. That's what we'll be doing today. And maybe with that, maybe we'll just go ahead and get started. As I say, anyone down in the audience who wants to hang out on stage and be able to ask me a question or tell me I'm wrong about something, which I sometimes am. Benjamin does a good job of that, but he's usually wrong. And we'll just proceed from there.
Wait, wasn't I completely right last week?
Oh, you are sometimes, very, very rarely, but it does happen. I'm totally willing to admit that it happens. It's like a stopped clock, right? It's the same thing, I think.
Sometimes being wrong is more interesting, anyways. So
yeah, it leads us
to better conversations.
Would you have done what you did, Andy, if Benjamin hadn't been wrong?
No. I think it was his idea. He deserves credit for that. The question he posed, and there was nothing wrong about that. That was great.
Yeah. And welcome, Robert, to the stage. Haven't seen you for a while. It's good to see you back.
Thank you, John. Nice to see you too. I'm
looking
forward to this. I'll stay as long as I can.
Okay, well, let's get into it. If you open the slides there at the top, you'll see... Oh, let's see. How's my mic? Am I too loud?
No, I think you're slightly overmodulated, but
okay. Yeah, I think I'm a little slightly overmodulated. Okay, so I think I've fixed that. All right, so let's, if you open the slide, you'll see there, this is Newtonian Mechanics 5. As I say, I was really motivated by this brain teaser more than anything, but it kind of fits into what we've been talking about, so I decided to make it the 5th episode of the Newtonian Mechanics series. Number 86. And there's links there on the page to all the previous Bites of Physics and a bunch of other things. And eventually there'll be a link to this room so that people can watch the slides and listen to the replay at the same time. And there'll also be a link to the YouTube that I suspect, Shamash, are we live on YouTube right now too?
Yes, sir. Link is in chat.
Okay, we're live on the Scientific Discourse channel on YouTube, courtesy of Shamash, who I really appreciate all the effort you go to do that as well, and make such pretty little images to draw people in. If only we were. I hope you're monetizing it. If you're not, you should. You deserve to monetize it. So that'll link will be there too. Okay, so on to slide 2. A little recap of last time. Last time we revealed that this mysterious weight force, I've really been trying to be, from the beginning, make clear that the weight force is really mysterious because it's the only force that we have dealt with and that we will deal with at least for some time that happens without any need for contact. That's a weird thing, right? It just acts on an object without even touching it. And that should be weird, right? We don't think it's as weird. I think technically these days, if we've gone to school at all, we probably don't think it's as weird as we should think it is, that something can exert a force on us without even touching us, whatever that means. And we revealed
Can
that...
I Feynman's objection here?
Yeah, go ahead.
Well, I mean, what you call touching is really just the introduction of what electrostatic forces between
Oh, now you're
objects.
just giving away the game. Yeah, you're trying
Oh,
to say
sorry.
that touching really is action at a distance, aren't you?
Well, I mean, we don't really know what scientifically it would mean for things to touch.
Yeah. No, that's entirely right. I've been trying to kind of lie about that. But you've revealed my lie, and so I'll just have to deal with the fact that I have been outed on that point. So that's true. Eventually, we'll learn that touching is really another action at a distance, just a short distance, via an electric force, which is also something that is mysterious. But for now, it's just touch. We're just trying to kind of put ourselves in the minds of somebody who doesn't know anything, is trying to grapple with all these things. So what we learned is that this mysterious force is obtained simply and weirdly by multiplying the inertial mass of an object by the gravitational field strength in the chosen reference frame. We introduced inertial mass in the context of Newton's second law, which we met for the first time last week. And it says that the impulse on an object is equal to its change in momentum. That's literally what Newton's second law says. Newton's second law doesn't say anything about acceleration. It says the impulse, which is the product of the net force and the time duration of that force, is equal to the change in momentum of a system, which is the mass of the system times its change in velocity. So, and using that, we found out that we can find the weight simply by multiplying by a thing that we call, that is called conventionally and weirdly, because we don't see any reason why it should really be about whatever gravity is, whatever gravity is supposed to be. It's called the gravitational field strength, G, and it's measured in newtons per kilogram, newtons of gravitational force, which is what a lot of people call weight. That's really wrong, because weight is the weight that we experience, is certainly not a Newtonian gravitational force, for reasons we talked about a little bit, and we'll talk about more. But that gravitational field strength can be obtained, weirdly, by simply releasing any object at rest from any known height and timing its fall. As long as it doesn't get going so fast that air resistance becomes a fact, it needs to really be acting, it needs to be falling under the influence of nothing but the weight force. That's the critical thing. And so it needs to not fall so far that it gets going so far that the contact with the air becomes a significant force as well. If that's the case, then we can simply use Newton's second law as it's written to find that the weight of an object is just its change in momentum, its mass, inertial mass, times its change in velocity, divided by the amount of time that it takes to fall. And we found last week that the change in velocity was twice the height from which it falls divided by that time period. So if I plug that in, I can see then that this thing that we call the gravitational field strength is nothing more than that 2h over delta t squared, as I indicate there at the end of that equation. That's how I can calculate the gravitational field strength, is simply by dropping an object from some height, timing its fall, and calculating it that way. But because the gravitational field strength is, in the end, a property of the chosen reference frame, any object will fall from a given height in the same time. We'll get the same value for any object. And so I can simply find the gravitational field strength by dividing the weight of a known object by the mass of that known object. And that's basically what gravimeters do. They have effectively measures the weight of a known mass, and it then tells us the value of G. And as I mentioned last time, these gravimeters in our phone call themselves accelerometers for a very good reason, but we won't, because we avoid the A word in here for now. We'll get back to that at some point. But our phone will tell us the value of
That was a
G
little
in
bit
our reference
confusing.
frame. Okay, go ahead and explain to me why. I know a lot of reasons why it might be.
Because you said the gravitometer, radiant gravitometer,
Gravimeter, I think is what it is.
measures
Yep.
measures a known mass.
It effectively
would
measures the
know.
weight of a known mass. Yeah, that's not what it really does, but that's what it effectively does.
It effectively measures the weight of a mass inside of itself.
Yeah, that's right. I mean, it's effectively hanging a mass from a spring and then measuring how much the spring stretches. It's not what it really
The
does.
question we had
That's
last
effectively.
week, to some extent, revolves around whether or not you can assess an unknown planet with a gradient gravitometer.
Well, this is not a gradient gravitometer. This is just a gravimeter.
Ah, okay.
It's just measuring
Now
G. That's all. Just measuring G.
So we can just tell the weight, and it doesn't really know anything. The size of the planet, the distance from
That's
the planet.
right. That's right. Yeah, that's right. No, and a good point. I mean, it's really important to point out. This is just measuring G at a point, and then assuming that that value of G is, reasonably constant in a local region around the point at which it's measured. So if I take my phone out of my pocket, it'll tell me what what G is where the phone is, and I'm just going to assume that that's pretty much the same as G where I am a foot and a half away from the phone. Something like that. Yeah, good point. So I've got a bunch of things there. People in different reference frames. Up the top, there's a guy bungee jumping. In his reference frame, his phone says that G is 0. And so in his reference frame, G is 0. But right next to him, there's a guy standing on the platform. His phone says G is 9.8 newtons per kilogram. In his reference frame, that's what G is. So the gravitational, this really drives home the point that I want to use here, that this gravitational field strength thing, the thing that the gravimeter reads, isn't a function of where you are in space. It's a function of the reference frame that you're in. That bungee jumper, in his reference frame, G is 0. In the reference frame of the person standing on the platform, G is 9.8 newtons per kilogram. So that's kind of weird, but that's kind of the way it works. If you want to take a modern perspective, if you want to kind of glue, as I'm doing here, a relativistic perspective on top of what is otherwise an intensely Newtonian background. We are going to use Newtonian gravity when we talk about gravity. We're going to use Newtonian mechanics. We're not talking about relativity. I'm just kind of gluing a little piece of relativity, the idea from relativity, on top of Newtonian mechanics, because I think it's profitable to do so, and it sets the stage later for understanding relativity a little bit better if you do that. And down below, there's 4 pictures of a guy in an elevator. In that first picture at the top left, the guy is. Let's just claim that the guy is in an elevator that is at rest with respect to the surface of the Earth, and that guy, his weight on the scale reads 700 kilograms. We say that's his weight. There's some other caveats to that, but for right now, we'll just say that's what the scale is reading. And the reason it reads that is because he has a mass of something like 75 kilograms. And when you multiply that by G in his frame, which is 9.8 newtons per kilogram, you get 700 newtons. But then there's several other pictures. They're right next to that at the upper right. He's in an elevator where the scale now reads, maybe you can't read it, I even can't read it, it reads 1,000 newtons. It read 700 newtons in that first frame. Now it reads 1,000 newtons. And that's because he's now in a reference frame where G is 14 newtons per kilogram. And that is because that is an elevator that is it might be moving downward or upward, but whichever way it's moving, its velocity is increasing in the upward direction. It might be moving upward and going faster, or it might be moving downward and going slower. But either way, the gravitational field strength in that reference frame is more than 9.8 newtons per kilogram. And so he feels heavier, and the scale says he is heavier, and indeed he is. His weight in that reference frame is more than it was in the first one. And then down there at the lower left, he's in an elevator which may be moving upward, may be moving downward, but over time, is moving more and more downward. If he's moving downward, he's speeding up. And if he's moving upward, he's slowing down. Either way, he feels less heavy than he normally does. And that's because in his reference frame, G is smaller than 9.8 newtons per kilogram. It's about 5.6 newtons per kilogram. So his weight is now 400 newtons in that reference frame. And then in the final reference frame, he's in an elevator where the cable has broken. And in the few seconds before his untimely demise, he notes that he weighs 0. He looks awfully calm there, given the fact that he weighs 0. He really should be kind of flapping his arms around and trying to get some semblance of balance. Okay, so I'm done with that slide. Any comments or questions before we go on? You'll notice that I'm being really I'm being kind of coy again as I do. I really want to drive home this idea that G, this thing G, even if you don't want to say that gravity is reference frame dependent, which you really should, I do want you to at least understand the utility of really talking about the gravitational field strength in this reference frame and how it affects the weight of that person. And how the weight does depend on that. Go ahead, Robert.
John, I was just wondering, the guy in the unlucky guy, bottom right, with the broken cable, would he ever sort of find himself stuck to the ceiling of the box as it plummeted?
Yeah, so that's a good question. And what do you think the answer is there?
It feels like he would, because if he's got 0G, then that puts him in a sort of astronaut place. And since the thing is plummeting with him inside it, you would think that that would be his natural resting place until the sudden stop at the bottom. Because as a farmer used to say to me, it's not the fall that kills you, it's the sudden stop at the bottom.
Yeah.
Is that right?
So that helped me understand a little bit where you're coming from. Astronauts aren't stuck to the ceiling, though, right?
That's true, yeah. So he'd be floating, would he?
Yeah, that's right. He is in the same situation as an astronaut. Now, there's this weird thing because the moment the cable breaks, there's still a force acting upward on his feet, which would probably tend to give him a little bit of a push as his body decompressed. He would have a little push off of the scale, and so he probably would, if he had enough time, come into contact with the ceiling, but only to bounce off of it, right? There'd be no sticking to the ceiling because the ceiling is just falling at the same rate that he is.
Right,
yeah.
Makes sense, yeah.
Right. So that was really good. That was a good little sideline. Thanks for that. Okay, any other comments before we move on? Okay, so let's move on to 3. We're going to, the thing that kind of motivated this was this brain teaser on buoyancy that we'll get to on the next frame. So I want to very quickly just deal with Archimedes' principle, which I think is a lovely thing. Archimedes was a really bright guy to kind of put this together so early. But it is, to state it, it's simply this, that an object that is immersed in a fluid, that's gas or a liquid, anything that can kind of flow around without sticking or, having a lot of viscosity, anything that's especially is basically hydrostatic equilibrium. If you're just sitting there and you're in contact with a material that can flow around you. An object immersed in a fluid is subject to a buoyant force which is equal and opposite to the weight of the fluid that object displaces. And it's really easy to just simply do the wrong thing when you're applying Archimedes' principle, but it is really simple, and it's a lot easier not to make those mistakes if you understand the simple derivation of Archimedes' principle. The buoyant force is nothing more than a contact force, but it's a weird contact force because it's a contact force that's distributed over the entire surface area of the object that is immersed. So there's a nice picture there. I stole this from the website that's down at the lower right because it's such a nice picture. I thought it really did need credit. We're going to put it looks like a little submarine or something that's immersed in a fluid. and you see the actual object on the right there, and then you see a little outline of the object showing the fluid that that object is going to end up displacing over at the on the left side there. And Archimedes' principle simply follows from the fact that if you think about, especially the object on, or sorry, the drawing on the left, the little dashed line that represents the fluid that will ultimately be displaced by the object, that fluid is in static equilibrium. It has a weight force, the mass of that fluid times the gravitational field strength in that reference frame. That's the downward arrow. And there's a buoyant force, FB, due to all of the fluid outside that dashed line that pushes on that fluid. It gets pushed from the bottom, it gets pushed from the top. That's kind of a pressure force all the way around the object. And the net result is, because it has to be, equal and opposite to the weight of that fluid. That fluid within the dashed line is, after all, just sitting there. And the only way it can just sit there is if the net force on it is zero. There's only one thing touching it, and that's the fluid around the outside. And that force plus the weight force that we've been talking about, the mysterious weight force, have to add up to zero. Otherwise, the fluid would be, I almost said accelerating. It would be changing its motion. The fact that it isn't means that that distributed contact force has to add up to a force up that we call the buoyant force, which is equal and opposite to the weight of that fluid. Now I take that fluid out of there, I take the fluid within the dashed line out of there, and I substitute an actual object that has exactly that shape. It's clearly subject to the same contact force and its own weight. So in the picture on the right, you see its weight downward, and the buoyant force is just the same force that it was in the picture on the left, which had to be equal and opposite to the weight of that displaced fluid. So now I can just say in general that when any object is put in a fluid, it's subject to a contact force, which we call the buoyant force, equal to the weight of the displaced fluid, but in the opposite direction. And then it's subject to its own weight, and that's it. That's the only thing touching it is the fluid, and so that's it. Now, of course, there could be other things touching it, but at least in this case, there aren't, and it wouldn't make any difference. The buoyant force would still be that buoyant force. So that's the argument for Archimedes' principle, and if you really deeply understand the argument for it, it gets harder to make a mistake in applying it. Any comments or questions on that one before we get to the brain teaser? All right. So with that in mind, we'll get to the brain teaser, which is going to occupy many, we're going to go through this very slowly in a lot of different ways to get to the end. This is a brain teaser that Derek on Veritasium dealt with. You can look this up on Veritasium. And in fact, you can, if you go to the link there in the ifuckinglovescience.com website, it has a link to the Veritasium episode that deals with it as well. And so the situation is pretty simple. Two identical containers of water are placed equidistant from the fulcrum of a scale on a table. A ping pong ball is fully immersed in, I should say they are containers of water. Ping pong ball is fully immersed on the right, and to keep it from popping up, which we all know a ping pong ball would, there's a fine thread. Now in physics, fine thread reads weightless and infinitesimally small, so I don't have to worry about any properties. We'll talk about that again in a moment. But you can see how I could make it the thread fine enough that the properties of that thread aren't much in terms of displacing water or anything else. So all those things are kind of important. So the ping pong ball over there on the right, and then on the left there's an iron ball that's also fully immersed, and dangling from a thread which is importantly attached to a support which is not on the balance. That support, the picture could have been drawn better. That support is on top of the same table that the fulcrum is. So the iron is dangling from a thread that's attached to a support that is not in any other way attached to the balance itself. And the water levels in these identical containers are the same. And I should have emphasized that both balls have the same size. They're both spheres of the same radius. The water levels are the same. And the question is, does the scale tip to the right or to the left, or is it balanced? And we can take a couple of moments here. It's interesting to me, if you go to the Veritasium video, Derek will just talk about it in a way that I think is the kind of way that will get you into trouble. He does reach the right answer, but it is really easy to argue wrongly for wrong answers if you follow a path different from the one we're going to follow in this lesson. Yeah, any comments or questions or predictions as we start? Because this is kind of fun. Get your predictions on the table if you like.
I say balanced.
You say balanced, okay. Anybody else?
I think I'm going to go with balanced. Just one question, for obvious reasons. Are either of those spheres actually flat?
We're not going there, Robert.
I think balanced.
Any other predictions? Cowards. Bunch of cowards here. Shamash, hi, Veda. Go ahead.
Hello. Yeah, I have a question. Is the weight of both the balls same or different?
Yeah, okay, that's a good. I should have made that more explicit. I am assuming that we know about ping pong balls and iron balls, and so they have the properties that we all know. But I don't mind being explicit. An iron ball is much heavier than a ping pong ball. And indeed, it's implicit in the drawing that the ping pong ball needs to be restrained from the bottom to keep from popping up, while the iron ball needs to be restrained from the top to keep from sinking. And it's probably, I'll even go so far as to point out that that is because the buoyant force on a ping pong ball is more than its weight. So the net force is upward, whereas the buoyant force on an iron ball is less than its weight, and so its net force is downward. Is that what you need?
Yes, thank you so much.
Yeah, thanks for the question. Don't mind being explicit about that. And welcome to the stage, by the way, Vita. I don't know if you've been in the audience before, but I think maybe you haven't been up here. Thank you for being here. Oh, and let's get Legend up here if he's still around. Sometimes I don't PTR enough.
We've assumed that the ping pong ball is massless, right?
No, we're not even going to assume that. But
okay.
it is the case, of course, that its mass is small. It must be because its weight is less than the weight of the water that it's displacing. That's why the buoyant force on it is greater than its weight. Okay, all these are good comments. I mean, just kind of solidifying it. We're really kind of using Archimedes' principle here. The weight that both balls are displacing in water is the same, evidently, but it's more than the weight of the ping pong ball and less than the weight of the iron ball. If that makes sense. Hopefully that makes sense. Okay, any other comments? Let me just take a quick look at the chat. Muhammad thinks the ping pong side will tip. Now that's okay, towards the ping pong side. So I think Muhammad is saying that he thinks the ping pong ball side will tip downward. He can correct me if that's wrong. So it's good. We've got we've only got two of the potential answers so far, right? Balance and tip to the right. I think that's what we've got. Yeah, okay, good. Muhammad agrees. Anybody disagree with that? Cowards.
I think the key is what you just said, John. It's the displacement. the amount of water that's displaced by both objects is identical, and therefore the weight of that displaced water is identical, and therefore the balance remains balanced, I think.
Okay. Okay. No, and that's certainly an argument that I think would convince a lot of people. I think you would probably agree it's not fully fleshed out,
Definitely
but
no confidence in it at all.
okay. All right. Well, good. This is
Ben's
fun.
here.
Oh, we
Ask
got
Ben.
yeah, we got a couple. We got several more people on stage. Oh no, let's see. Oh no, we don't. Sorry, I was looking in the wrong place. But yeah, let's ask Ben. Ben, I don't know if you've been here long enough to have an opinion as to which way this thing will tip on slide 4.
I've
Yeah.
just arrived. Give me 2 seconds. I haven't even got the slides
Okay.
open. Slide
That's
4.
okay.
Yeah.
Take a moment. We'll talk to Mohammed here.
Oh, I
Hey,
see. Okay.
Mohammed, welcome to the stage. Did you want to elaborate? Good.
Yeah, Can you hear me okay?
Yes. Uh huh.
I'm assuming this is, I didn't catch the very beginning of your question. I'm assuming the same volume of water on both sides, right? The container's the same.
Yeah, I notice I didn't say that explicitly, but how do you know that it's the same volume of water on both sides? If you go back to slide 3 where I specified it, where I specified things. Oh, no,
sorry,
I'm sorry. Slide
I didn't
4.
even see
Sorry,
this.
slide 4. Yeah. On slide 4, what did I say
I
that
didn't
makes it
even
clear
see
that the
this.
volumes are the same?
I didn't even see the slide. I was on podcast mode doing
Oh,
other stuff,
okay,
so seeing
okay.
the question. I made an assumption. Am
Oh,
I
okay,
wrong
that's
in
fine.
making that assumption?
No, you are right because what I said is that the containers are identical. And then I said the balls that are displacing fluid are identical. And then, crucially, I said the water levels are the same in both containers. The only way that could be true is if there was the same amount of water in
Yeah,
both
exactly. So
containers.
I assumed that.
Yeah,
I guess
yeah,
my
that's
thinking
right.
here is, my thinking is you have two containers on both sides, same amount of water. Let's remove the balls. So the system is in equilibrium because you have the same masses on both sides. Now you
Yeah,
introduce the ping pong ball on one side, and I think it's a material, whether it's submerged or not submerged. The mass of the ping pong ball, ergo its weight, is added to one side of the system completely. Doesn't matter if it's submerged or not. If you are weighing it, I assume that additional mass it's the same. But in this case, anyway, it's submerged. If it's submerged, it displaces an amount of water, um, which has a weight, but that's part of the system. So I'm not thinking about the forces. On the other side, you put the iron ball or metal ball, but it's also submerged. They're the same size, so it displaces the same amount of water. So if there is any effect due to the amount of water, meaning the weight of the water, it will be the same. Crucially, though, you're saying that the metal ball is suspended, which means its weight is not being supported by the water, the way I understand it. So from that side of the system, there'll be less weight as compared to the ping pong side, which, even though it's light, it adds some incremental amount to the force subjected on the scale. And so I would say that it would tip towards the ping pong.
Oh, interesting argument.
So that was really well said. And
Yeah.
let me just say that whether that's right or wrong, I think that was a very
Yeah,
compelling
me.
argument. Yeah.
Well, thank you.
Yeah, no, that's really nice. It's nice. It's rare that I hear a full argument as compelling and completely made as that one. And we'll see in the end whether it's right or wrong. But it doesn't matter. It was really good. Ben, what do you say?
So I had a look at the diagram. I'm going to do a really quick answer off the top of the head. I'm going to say that um, the water must be applying an upward buoyant force on the iron ball. Therefore, the iron ball must be applying an equal and opposite downward force on the water. The iron ball is certainly not going to. Well, that's it. That's all I need to say, really. So the left side will go down.
So you think, okay, good. So we finally have somebody who thinks, so now we've got all the bases covered. We have people who think it'll tip to the right, people who think it'll tip to the left, and people who think it'll stay balanced. Has anybody changed their mind? Even after, is it Said? Is that right? Is that your name, Said? Am I saying it correctly?
It's
Yeah.
Said. That's right.
Even after Said's compelling argument, did nobody change their mind to
Almost,
agree with him?
almost, but not quite.
Hey, John,
Okay, so you almost got Robert. Yeah, go ahead. Go ahead.
I just now sat down and opened up the slides. So, which slide are you
We're
discussing?
on 4. We're
Okay.
looking at the brain
Oh,
teaser
come
setup.
on, hero. Jesus Christ.
I know. I'm
Coming late to
I was
class and
here.
not
No,
opening
I
your
was
books.
here on time. I just wasn't paying attention.
Sir, what are we talking about today?
Is this going to be on the
Can you
test?
just catch me up? Can you just sum up everything you just said?
Okay.
So,
So
John,
you can. Yeah, go ahead, Ben.
just to restate that, just to make sure it's more complete. So in the right-hand case, I don't care about any of the internal forces. I don't care about any buoyancy on the ping pong ball or anything like that. That's what I call internal forces to the system. And on the left-hand ball, there must be a buoyant force upwards on the ball from the water. Therefore, the ball must be pushing downwards on the water by Newton's first law. Sorry, Newton's
Okay,
third law.
that's
Sorry,
right.
Yeah, that's it.
So you're identifying what you think is an additional downward force on the left, but there is, of course, an additional downward force on the right in the form of the ping pong ball too, right? You wouldn't deny that.
No, the mass of the ping pong ball and the arm and stuff.
Yeah.
Yeah, but you
Right.
saw. But you haven't told us anything about the specification of the ping pong ball or the arm, etc. And the mass of
I've
the
told
ball.
you one thing.
Maybe
We don't
I have told you
I've
one
only
thing.
looked at slide 4. I've only just arrived.
Yeah.
So
Yeah.
what have you told us?
Let's see. And now, and Legend, I've invited you up a couple times. See if somebody else wants to invite Legend up too. Maybe we'll get him. up on
I'm
stage.
trying to, but
Okay.
apparently you have to either go out and come back or click on your picture and accept the invitation.
Yeah. Okay. Anyway, that's fine. Any other comments on this one? Yeah, go ahead.
I've
Andy.
reviewed the diagram. What have people said so far? Have you voted on?
Oh, then you really
I know,
are you
I
going to
know.
do this?
Okay.
Are you-
I think it balances.
Okay, yeah, good. In answer to Ben said I hadn't told anything or something, but notice I have told you one thing, and I have told you effectively that the weight of the ping pong ball is less than the weight of the fluid displaced, and the weight of the iron ball is more than the weight of the fluid displaced. The picture tells you that because of the way they're suspended.
We don't need to know anything else here, I think, because we no matter how heavy the iron ball would be, it would be experiencing the same buoyant force from the water, no? Because it depends on the volume, not on the mass.
Right. The volume displaced is the same, and Archimedes' principle says the buoyant force is the weight of that volume of water.
Have you made a prediction, Shamash? I haven't heard one yet.
Have I made a prediction?
No, Shamash.
Oh no, I was the first. I said it balances.
Yeah.
Oh, okay. You're with me then. Cool.
Yeah. Okay, well, let's move on, because what I want to do on the way to understanding the answer, I want to exhibit how profitable it is. In fact, I would say almost. Oh, let's see. Somebody's Said. Can you mute up?
Oh, I'm sorry.
Yeah, that's fine. On the way to the answer, I want to show how profitable, I would say almost essential it is to use the method that we used in in analyzing static equilibrium. That is to say, pick a system, count the forces, then identify them, and draw force diagrams. That's what we're going to do here for lots of different situations. So starting on 5, I want to start by, I'm going to do 2 at once. I'm going to do one force analysis for the system consisting of the iron ball, and another one for the system consisting of the ping pong ball. And so I've drawn little red dotted lines around so I can follow that red dotted line and identify anything that touches the iron ball. And so I'll just ask you, how many things touch the iron ball?
Depends if it's over age or not, but 2 things.
2.
2 things, right? What are they?
The suspending thread and the water.
That's right. That's the only thing that's touching the iron ball is the suspending thread and the water. What about the ping pong ball?
The tethering thread and the water, 2.
Yeah, so it's the same thing, right? Something that's holding it and the water. So there's 2 contact forces in both cases, and therefore we know that there are 3 forces acting on each of those things. Those 2 forces and their own weight, that mysterious weight force. So on the next slide, then, I'm going to just draw the force diagrams. So let's go to slide 6. And I think you'll see, I think we can all agree on this, right? Both of them have a weight force that's downward. Both of them have a buoyant force that's upward. And crucially, that buoyant force is the same on both of them. And the iron ball has an upward force due to the tether, and the ping pong ball has a downward force due to the tether. So given that information, I need to draw force diagrams, and hopefully you'll see the iron ball has to look like that. It has two upward forces that have to equal the one downward force. The weight is rather large, and it's equal in magnitude, and this will be critical too, to the sum of those two forces. The directions are important when we're talking about vectors, but having drawn the vector diagram, I can just say that the amount of weight is equal to the tension in the tether plus the buoyant force. That's the only way that vector diagram makes sense. Whereas over on the ping pong ball side, I have one upward force, the buoyant force, and two downward forces. The tether is now pulling down on the ping pong ball, and of course the mysterious weight force is downward as well. So those two forces have to add up now to the buoyant force, which is the same. Okay, so I've kind of drawn those arrows. In fact, I'm sorry, if you're looking this on your phone, it's probably pretty hard even to see that. But the one thing I really want to take away from this is the ping pong ball. And so I'm saying up there at the top of this slide, notice that the ping pong ball analysis tells us right away that the buoyant force on both balls is equal to the sum of the weight of the ping pong ball and the tension force in the ping pong ball's tether, the thing I'm calling TPP. And that's what I've drawn. I've put up there at the top. I'm going to call out a few relationships as we go through this. The buoyant force on both balls is equal to the sum of the tension in the ping pong ball tether and the ping pong ball's weight. Any comments or questions on that? And notice, I mean, I hope already you're kind of seeing, this is kind of nice, right? You might not immediately have seen these relationships, but we get them very quickly by simply choosing a system and then counting the number of forces, identifying the forces, and drawing the force diagrams. I think you'll agree that this is the only possible way those force diagrams make sense. Clearly, the iron ball has two upward forces that have to equal the one downward force. And clearly, the ping pong ball has one upward force that has to equal the two downward forces in magnitude. Okay? Comments, questions? If not, yeah, go ahead. Benjamin, your mic is shit. I don't know. Or you're anyway, you're kind of scratchy. There, better. Good.
I am gonna break up, and I'm gonna break up in a minute because I'm gonna do that Wi-Fi to leaving the house.
Well, you're good for the moment, so why don't you go ahead? You must have just left the house. We lost you, Benjamin.
Recently, by
okay, we lost you totally for that. So start again.
Okay, am I back now?
Yep.
I even stopped the car to try to stop it from happening. There's a weight on an elevator, which was recently part of a fatal accident by Rob Holland, I think. And the elevator weight pulls down on a part of the elevator. And maybe, are you familiar with this at all? But they didn't use a spring. They could have used a spring. They could have used counteracting.
So I'm not. No, I don't really understand. Are you talking about the counterweight of an elevator? I don't really understand what you're talking.
No,
Okay.
no, no, not the counterweight in an elevator, but it is an elevator counterweight because on an airplane, the elevator is the flap at the back of the airplane that
Yeah.
points the airplane in a new direction, up and down.
Okay, so you're talking about a plane elevator, not an elevator
Yeah,
elevator.
airplane. And
Okay.
there's a counterweight. And it's different than a spring would be because they would have used the spring. Springs are lighter. It's different than a
Right.
aerodynamic interaction because they
Right.
would have used it's a weight reaction.
Because it's a so it presents a constant torque or something.
Well, I doubt that it's constant anything, but it certainly presents a reaction mass and a reaction weight on the elevator. And it would be really helpful if you, as a physicist, could explain to us as pilots how that works. And it seems like it's about what you're talking about here.
So, yeah, let me not do that right now. I'm not sure I even understand this. It seems like something which is intended to bring the elevator kind of back to its passive position or something. Is that what it does?
Those are also there to add mass to affect the to reduce the possibility of flutter. So it's there for like a dynamic reason as well as
Give it inertia. Yeah. Okay. Well, I don't really understand that, but maybe we can talk about that in the afterwards. It sounds like it's a little bit apart from the whole buoyancy thing here.
Flutter has killed a lot of airplanes. Yeah.
Well, and records, for that matter. So that's another thing, though. Oh, okay. Sorry, that was silly. Let's move on to slide 7, where I'm going to choose different systems. Now I'm going to choose the water only. On both sides, I want to analyze the water
all I can say to
only.
that is wow. All I can say that response is wow.
Yeah, yeah, good. I should have thought of that. That's good. I like that. So now on slide 7, we're just going to look We're going to look at two systems. The two systems shown, just the water in each case. So let's start with the iron. How many things touch the water? On the left. It's a little. So there's one little thing here we might have to deal with. You might come up with what I'm going to consider the wrong answer, but it's not really wrong. Somebody name something that touches the water.
The ball,
The ball touches the water.
the wire,
Okay, good.
and the beaker, the actual container.
Okay,
Some
good.
might say the container.
The container, right? Yeah. So the container clearly touches the water. The ball clearly touches the water, and I think it's true that the thread clearly touches the water. And maybe we should say 3 things. Can anybody think of another thing that's touching the water?
The water touches the water.
The water touches, but that's of course when we talk about a system, we don't worry about that. Now, I might mention it's probably important to understand the atmosphere as well, and that's true. And I didn't even think about it when I was drawing the slide. I really should have, and yeah, I really should have. So that's kind of a mistake. And I'll own up. I'll tell you how that changes things on the next slide. There are 4 things touching the water: the atmosphere, the thread, the ball, and the container. What about on the right? Same thing, I think. Would everybody agree it's the same thing? The container, the ball, the thread, and the atmosphere. 4 things touching the water.
Yeah.
Right. So I agree with that. I think that's right. Now, so on the next slide, I'm going to identify those forces and add them. But I want to tell you right now why I'm not including 2 of those. I'm not including the thread, partially because I tried to make the thread kind of negligible. I talked about it being negligible. And the only really important thing is that I don't want to worry about the fact that it's touching the water, and the water is really, in some sense, providing a buoyant force to that thread equal to the weight of the water being displaced. Can we all just agree that the thread is really tiny? There's virtually no buoyant force of contact, in other words, with the water, and so there's not going to be any vertical force. There is kind of a side. There's more of a force pushing on the thread from all sides from the water, but all those forces are horizontal forces, and they all, I think, pretty clearly cancel out. There's just as much force on one side of the thread as there is on the other. The thread is getting compressed at some level by the push by the water, but it's not providing any net force to the thread, and so the thread isn't providing any net force to the water. Hopefully, this convinces you that I don't have to worry about any force provided, no force of contact between the thread and the water. It's not because there isn't. There actually is a force, a non-zero force of contact, but I've endeavored to make it completely negligible, and so I am going to neglect it. Now, when it comes to the atmosphere, it is true that it really should have included a downward force on the water due to the atmosphere pushing down on it. But maybe you'll let me just neglect that for the moment anyway, even though it is absolutely not negligible. And we can talk about that more at the end if you want. But I think you could also agree that if I wanted, I could have this take place in a vacuum, except for the fact that the water would eventually evaporate if it were in a vacuum. Maybe I do it very quickly in a vacuum before the water evaporates. Anyway, we'll talk about the atmosphere force, which I honestly hadn't even thought about. It escaped. This is how easy it is to forget about a force of contact.
Would it not be symmetrical on both sides, the wire and the atmosphere, so it won't really matter for our question?
So I think it's easy to make the argument that the atmosphere will be the same force on both sides. I think it's not quite as easy to make the argument that the thread will be the same unless I modified the problem statement to say that the same amount of thread is in the water.
Yeah,
in both
we could
cases.
Always make it happen, right? It's not
Yeah,
that
I
hard.
could make it happen. That's
I mean,
right.
it's way easier
That's
than making it in the vacuum.
Yeah. Well, but the vacuum thing's kind of another issue. The thread is one issue. The atmosphere is another issue. I have to come up with different ways of neglecting them. I think the thread is easy to come up with ways to argue that it's negligible. The atmosphere is not. That is going to change things, and I apologize in advance for just not having included it. I should have. It wouldn't change the bottom line, but it will change the diagram that I'm going to show you on slide 8. Okay. And by the way, Legend's up on stage. Legend, did you want to say anything about a previous slide or this slide before we move on? Welcome to the stage. I think Legend, it must be a little bit busy. He's been took a little while to answer the call to the stage, but feel free, Legend, when you get a chance to say something. And say, did you want to say something? I think I see you raising your hand.
Yeah, I'm just, I guess, originally when I understood you to say that the metal ball is being suspended, but I don't think I heard you say that its thread was massless or negligible. I mean, did you say that? I heard you say
I made some comments at the beginning to say that for reasons that I would get to later, later being now, I did want to make the thread really fine, a fine thread. When you see in a physics problem a statement like fine thread, that's understood to mean massless and negligible. Yeah, so that's right.
I guess my question here was, when you said suspended, I assumed that because it's a metal ball, it's obviously not going to float. Right. Likely not to float. I mean, it's a dense metal ball, I'm assuming, so it's not going to float. So I understood you to mean that it was suspended, as in there is tension in the thread. Is that what you meant, or did you just mean it?
That is what I meant. That's right. Okay. All right. That is definitely what I meant. And it really was. I at one point, in answer to somebody else's comment, I pointed out that I am kind of depending on your understanding, but I'm not unhappy about making it explicit that the iron, obviously the buoyant force on the iron is not enough to keep it from sinking, which means immediately by Archimedes' principle that its weight is greater than the weight of the fluid that it's displacing. And in the case of the ping pong ball, it's just the opposite. It has to be restrained from popping to the surface. That means immediately that its weight is less than the weight of the fluid that it's displacing. Yeah, so always good to revisit those things. Okay, so let's move on and draw the diagrams. And notice I'm only going to draw one diagram here because it's the same in both cases. In both cases, we have the same weight of the water. It's the same amount of water, so it has the same weight. We have the same buoyant force. Oh, and by the way, I should say, I shouldn't, let's get to the buoyant force in a moment. We have the same force of the container on the water. Why is that? That's a good question. Maybe let me just assert that, and then if somebody wants to challenge that, we can talk about it. And I have the same buoyant force. I have the same buoyant force on both objects. Now, that buoyant force is the force that the water exerts on the object. And so the force that the object is exerting on the water is negative the buoyant force. That's why I've drawn it the way I have. That downward force on the water is the reaction force to the buoyant force that the water exerts on both objects. Both objects are subject to an upward buoyant force. That's the force of contact that the water exerts on the ball. And therefore, by Newton's third law, the ball must exert a downward force on the water. Ben was alluding to this earlier when he was talking about it. Both balls, he talked about the iron ball, but both balls exert a downward force on the fluid around them equal to the opposite of the thing we've been calling the buoyant force. And so if only for that reason that there are, at least what I've drawn here, there's only two downward forces, then the force of the container on the water must be equal in both cases to the sum of those two, because the red and the blue forces are the same in both cases. So the upward force of the container on the water must be the same. Now, I made a mistake in drawing this diagram, as I omitted on slide 7. So how should I have drawn this force diagram? How would it differ if I hadn't neglected the force that the atmosphere is exerting on the water?
That'd be a third arrow pointing downwards.
Right. There'd be a third arrow pointing
the
down.
black arrow would have to be a little bit bigger as a result.
That's right. And it would be the same downward force in both cases, so I could still get away with one force diagram. I would still have the upward force being the same in both cases. So that's really the only difference, and I'm kind of glad because, in fact, I'm not going to use this relationship for anything in the future. So maybe that'll make us happy. At any rate, good. So I think we've dealt with the force of the atmosphere. Any comments on this before we choose a different system and look at what's going on? Okay, so on slide 9, now I want to look at the two containers, just the two containers. So let's start on I think you'll see that in terms of number of forces, it's kind of the same. Maybe not. Let's actually start on the right this time. Well, let's start on the left. Sorry, let's start on the left. The iron ball. But I want to just focus my attention on the container. I've drawn a dotted line now that is kind of outside the container and then inside the container. I want to go all the way around that border and ask how many things touch the container. It's a little tricky.
There's two things I can count.
So what are they?
The water touching the container and the balance from the outside.
Okay, right. So the balance that it's resting on is touching the container. The water inside the container is touching the container. I actually see now that there's a third thing touching the container. What's that?
Air.
Air, that's right. And so I'm going to quickly dismiss that once again by saying, yeah, that's true. It is. And in fact, the air is even exerting an upward net force on the container. So I really shouldn't have even neglected it. So I have to kind of like quickly argue some words. I'm going to just admit that I did neglect the air on the container. And I shouldn't have. I could have. And if anybody wants to call me on it on the next slide, I may call myself on it. We'll see. But the only things I'm going to include are I'm going to argue certainly that the force that the air exerts on the container is negligible. We can argue that maybe if you want. I think it's pretty easy to argue that. I am going to neglect it. And enough said for now. What about on the right? How many things touch the container on the right?
So the water, the balance, the air, the bottom of the thread.
And the bottom of the thread. That's right. There is one more force acting on the container on the right. Whatever you think, there's one more force acting on that container that's not acting on the container on the left. That's a really important difference. Right? The thread is, and what is what is the force exerted by the thread on the container? Is that an upward force or a downward force?
It's hard to push on thread.
It's hard to push on thread. I was going to say that's an adage. That's a physics adage. You can't push a rope. That's a really important physics adage. So threads can only pull, and therefore the force that it exerts on the container is up. Thank you, Andy. Exactly. I was going to say that myself if nobody else said it. Okay? So what do I say? I'm going to say two forces on the right. The scale is pushing on it, and the water is pushing on it. I'm neglecting the atmosphere. It's true. We can talk about that if you want. And then on the right, three forces. The scale is pushing on it, the water is pushing on it, and the thread is pulling on it. So let's see what that looks like if you're ready to go on to the next slide. Any more comments on this before we move on? Okay, so on slide 10 then, let's start with the iron side, the left side. The scale exerts a large upward force. That's a support force. It's the kind of force that we called a normal force. It's perpendicular to the surface. It's an upward force being exerted on the bottom of the container from the scale. So I'm calling it N sub L to mean the normal force on the left. And I claim that that force plus the force that the water exerts on the container plus the weight of the container have to add up to zero, right? Because I always add to the however many contact forces, I add the mysterious weight force, and it all has to add up to zero. Now, the force that the water exerts on the container is just the opposite of the force that the container exerts on the water. That's what we met on in the previous, when we used our systems, when we were looking at the water as the system. So that's why I put there minus F container on H2O, C-H2O. So that's the reaction force to the force that the container exerts on the water. It's equal and opposite to that force. So the water exerts a downward force on the container. Does that make sense to you that the water is exerting a downward force on the container? I hope it does. Because clearly,
in the current formulation of the system, yeah. I mean,
yeah,
the weight of the water is not a property of the water, but in our current formulation, we're taking the container as a system. So yeah, you could say that.
Right. Clearly, if I put water in a container, there's more downward force on that container than there was before I filled it with water. It's weird a little bit because the water is clearly pushing out on the walls of the container as well. I made an argument about those before saying, that's all going to cancel out because there's going to be as much force outward on one side as there is outward on the other side at every level. So that should all kind of cancel out. I don't expect any net horizontal force on the container due to the water. I expect the net force due to the water on the container to be downward. And I expect it to be equal and opposite to the force that the container exerts on the water, which is why I used that symbol, the same thing we met before, and I just put a negative sign in front of it. Okay, so on the left I have the scale exerting an upward force which is equal in magnitude to the sum of the two downward forces, the force that the water exerts on the container and the weight of the container. It's a little confusing, the way my notation there might be a little confusing. Now, over on the right with the ping pong side, it's a little more complicated. Once again, there's the force that the scale exerts upward on the right. That's what I'm calling the normal force on the right. It's a big force. There's the downward force that the water's exerting on the container that I'm labeling negative force of the container on the water. And there's the weight of the container. Those are two downward forces. Now notice those two forces are the same on the left and the right. The force that the water exerts on the container, the force that the container exerts on the water is the same in both cases. The weight of the container is the same in both cases because they're identical containers. But then in addition, there's an upward force on the bottom of the container, which is equal in magnitude to the tension in the thread. And we've met the tension in the thread before when we talked about the ping pong ball that we called tension PP, T sub ping pong. That was the downward force that the thread exerts on the ping pong ball. So here I'm showing the same force. It's in the opposite direction. It's the negative of that. It's the tension in the same tension in that string, but now it's an upward tension exerted on the container. And you can see from the diagrams then that the normal force exerted on the right is less than the normal force exerted on the left. Because on the left, the normal force has to do all of the countering of the force that the water exerts on the container and the weight of the container. Whereas on the right, the upward force from the scale is helped, strangely, by the fact that the thread attached to the ping pong ball is pulling up on it. Right? The scale doesn't have to push up as hard because the ping pong ball is helping to lift the container because it's attached to the container and it's pulling up. That's kind of a weird way of talking about it, but it's really true. Right? The upward force on the right doesn't have to be as much from the scale because that thread is pulling up on the container. And you might say, yeah, but the ping pong ball is just sitting there and it's pulling down on the ping pong ball, but I'm not talking about the ping pong ball. I'm talking about the container. The only force acting on the container that has to do with the thread is an upward force due to the thread. So that's a little bit of a weird diagram, and I want you to take away two things from this. I've just shown you that the upward force from the scale on the right must be less than the normal force from the left because of the fact that the downward forces are the same in both cases.
So there's
and
I'm sorry.
And by that TPP. So I say notice that the normal force on the left is greater than the normal force on the right by the amount of TPP. There I'm not putting the negative in, I'm just saying how big NR is plus how big TPP is has to be how big NL is. Go ahead, Andy.
Well, there's a bit of a pulling oneself up by their bootstraps
Yeah.
kind of a thing going on here, and I can't believe that the pulling up on the container is not canceled out by the pulling down on the ping pong ball.
Right. It feels like that, right? But and this is a really good example of why it's so important, especially in buoyancy problems, to use this method where you're just rigorously attached to a system that you've chosen. Doesn't matter what's happening to the ping pong ball, because the ping pong ball is not the system we're looking at. We're looking at the container. And the only thing that matters there is there's a thread pulling up on it. But you're right. That's exactly the trouble you can get into if you don't rigorously follow a method like this. It does feel like you're pulling yourself up by your bootstraps. Okay? So we're almost done. We're going to look at one more system. Actually, it's going to be a different system on both sides.
John, is this intentionally pulling teeth? I have got a one page. Pick the system right. It's one page and two equations. Can I share that as a PDF at some appropriate point?
Yeah, absolutely. And I
Because
think you'll see it's probably pretty much my bottom line as well.
Yeah, I mean, okay. I'll share that in the chat in a second.
Yeah, do that, and feel free to. We're right at the point where we're going to get to probably what you're sharing, because I only went through this really to show you that how much information you can get from looking.
It's wonderfully rigorous and wonderfully general. I think it's really important to say the way you've done it. It will work in. I mean, I might have done it wrong. We'll find out. But I look at that. I draw the right force, and it's very obvious immediately. But I think I've earned the way to that by doing thousands of these types of problems and earning an intuition. And it's an open question for a very interesting discussion at the end, which way people should learn, whether you have to earn the right by doing a whole bunch of problems and then learning how to pick the system right so you simplify it, or whether you need to, whether you can go straight to that. I don't know the answer, actually. But we'll talk about that.
I think what happens often in a situation like this is you don't know at first what system is going to be the most profitable and direct way to the answer. But once you find it, you realize, as we'll talk about, and as I'm sure you will say as well, there's a really simple way of explaining this that makes it immediately clear. But I don't think you can get to that. I don't think you can really appreciate that until you have done a few problems this way. Just as you say, I think it's just that. So let's in this last example. So on slide 11, I'm picking slightly different systems, but these are systems probably that with a little bit of the kind of understanding that Ben is alluding to right now, just kind of saying, okay, what really matters here? This will probably be the most direct way to the answer. So what I'm going to do then on the right, I'm going to do a really simple thing. I'm just going to make the system be everything that's sitting on the scale. That's what it is on the right. Everything that's sitting on the scale. And on the left, I'm going to do pretty much the same thing. Everything that's sitting, it really is in some sense everything that's sitting on the scale, but I'm going to actively make clear that I am excluding the dangling ball from my system. It's just the container and the water. That's it. It's the container and the water. That's it on the left. On the right, it includes the ping pong ball because it's everything that's sitting on the scale. But the left is a little different because it's dangling that ball into the water, and that will be crucial, as I'm sure Ben's going to say. And I'm going to exclude the dangling ball. So let me ask you then, let's start with on the right. How many things are touching the system on the right, the ping pong ball side? How many things touch it? And let me just say, I'm going to just rule out the atmosphere. Okay, we can talk about what the atmosphere does. It won't change the answer, but let's just rule out the atmosphere. How many things touch the system on the right?
On the right, just the scale.
Just the scale. One thing. That's it, right? Now on the left, how many things touch the system? on the iron ball side.
Okay. So there is the scale on the left, but I think we have to include the iron ball and the thread as well.
That's right. Then we're going to, so the iron ball and the thread also touch it. I'm going to neglect the thread for the same reason I've always neglected the thread. So I'm just going to say two things are touching the system, the scale and the ball. Right? Okay, so I've got two things touching the iron on the iron side and one thing touching on the other side. Let's go to slide 12 then and draw the diagrams. So let's start on the right, on the ping pong ball side. One thing touching the system, that's the same thing we already, it's the normal force from the scale, NR. We've already met that force. That's the same force we met in the last system. And then there's the weight of the system, which I can break up. The system consists of three things: the container, the water, and the ping pong ball. Those are all parts of the system. They all have this mysterious non-contact force acting on them. They're all downward. So I have the weight of the water, the weight of the container, and the weight of the ping pong ball. So that upward force, due to the one force of contact, simply has to equal the weight of the system. That's it, right? Now on the left, what do I have? Well, I've got a similar kind of a thing. I have the normal force. So I have the same normal force, the NL that we met before, upward force that the scale is exerting on the container. And then I have the weight of the system, which now is just two things: the weight of the water and the weight of the container. That's all. The system is just the container and the water. So I have those two downward forces. But then there's the force of contact that the iron ball exerts on the water. And that's just as we've seen before, that's the opposite of the force that the water exerts on the ball. The force that the water exerts on the ball is the buoyant force, so the force that the ball exerts on the water is the negative of the buoyant force. It's a downward force of equal magnitude. So what do we see in this diagram? In this diagram, we see that why is NL bigger than NR in this diagram? It can only be bigger if the buoyant, notice that WH2O, WC are the same on both sides. The only way NL can be bigger than NR, which it is if the buoyant force, the magnitude of the buoyant force, is bigger than the weight of the ping pong ball. But we know that the magnitude of the buoyant force is bigger than the weight of the ping pong ball. That's why we had to tie it down to keep it from popping to the surface. So once again, we reach the same conclusion. I've written there, notice what I've written is that NL minus B, since that's got to equal to the WH2O, that has to equal the weight of the water plus the weight of the container. If I subtract the buoyant force from the NL, I have to get the weight of the water in the container. Whereas on the right side, if I subtract the weight of the ping pong ball from NR, I have to also get the weight of the water plus the weight of the container. So those two things have to equal themselves. And that's really just saying NL is bigger than NR because B, the buoyant force, is bigger than the weight of the ping pong ball, WPP. And on slide 13, I just kind of belabor that point. I don't know that I even want to go through this. I just want to point out, I'm just pointing out on slide 13 that either way you look at it, using the results that I called out, we find out that the normal force on the left is bigger than the normal force on the right by the tension in that thread that holds the ping pong ball down, which is itself, of course, the
so I
difference
understand your
between
whole point here is that the up forces have to match the down forces. Is that your point?
Yeah, that's right. That's been the point in it with each system. I have to have a net force of 0.
So you can understand this concept
Which concept? The elevator?
that the ups have to match the downs, and they have to be a net force of 0.
That's right. I do. I really do understand that.
That will come into play later.
I know you're going to try to challenge me on my relativity thing. That's fine. You can do that too, because we are doing Newtonian mechanics after all. Okay, so let's see. I think so. Answering the question just quickly on slide 14, I haven't really just said it, but of course the force that the scale exerts upward is just the reaction force to the force that the container, that everything is pushing downward on the scale. If NL is bigger than NR, that can only be because the scale is being pushed on harder on the left than it is on the right. And if the scale is being, if you push downward on the left harder than you push downward on the right, the scale will tip to the left. And so the answer is that the scale does tip to the left. It's not balanced. It doesn't tip to the right. Notwithstanding Said's really wonderful, compelling argument, it was wrong, right? And it's just, I think it's really a testament to how compelling an argument you can make and how wrong you can be led making arguments like that. And really was. I mean, I'm not kidding when I say that. It was a beautiful argument and it was wrong. And that is what can easily happen with these buoyant force kinds of things. Ben, did you want to give your spiel now? It's time for Ben.
Yeah, just take somebody else first. I just want to make the single page a bit more elegant than it is.
Okay, good.
Yeah.
Go ahead, Robert.
Yeah, I was just going to. I get that. Beautifully explained, and I don't think it was pulling teeth at all. And I love the force diagrams. I really did enjoy that whole thing. The only point I would sort of make, and this isn't to challenge the result, it just there's a moment where it feels that you're cheating a bit.
There's many moments.
I can fix that. I can easily fix that.
But the one that I wanted to point out was that the right at the beginning and all the way through, the thread is infinitesimally small and can therefore minute and all the rest of it, and then can therefore be safely ignored, except in the point where it's crucial for the argument or the answer to become clear, which is where the ping pong ball thread is actually pulling upwards, which I totally get and I totally missed the first time round. But that's the only point where the neglected thread all the way through becomes not neglected.
Well, it is true, but this is really common, right? We don't neglect the force that a thread exerts. That's important, right? There's nothing negligible about the force that it exerts, but it is often useful. It's not I can include all of those little negligible forces if I want and make the same point. But it is really literally the case that the weight of the thread is really negligible. Doesn't matter very much. And the volume of the thread doesn't matter. Yeah. But the tension in the thread, that's a thing. That's a real thing and can't be neglected.
Matter. I get it, yeah.
Yeah.
So everything else
right.
doesn't, but the force does. Yeah, I see that.
Right.
Cool. Okay, thank you.
Yeah.
Can I ask?
Go ahead, Andy.
An alternative. What if you replaced the infinite or the negligible thread with, this might be a little less plausible, but a negligible but sufficiently stiff rod, little piece of carbon nanotube or something, and push down on the ball on the right instead of pull down on it? I think you would get exactly the same result.
Let's see. Let's have to think about.
I should say, would you get a different result?
Yeah. So yes, you would. And let me kind of elliptically get to that by talking about suppose I just put two identical containers of water, just filled two identical containers of water on both sides of the scale. There's no balls at all. It's balanced etc. And now I stick a finger in on the left. What happens?
This is exactly what I've been thinking about this whole time. I think there's a buoyant force pushed upwards, so that must exert a force on the container downwards.
That's right. That's right.
Yeah.
So if I just stick my finger, I just have two identical containers of water, no balls, anything. I stick a finger in on the left, and this is a really wonderful physics demonstration. I used to do this. I stick my finger in on the left, and that left side goes down. I push that container down by putting my finger in it. And it's easy to see why, because the container's pushing up on my finger. That's the buoyant force. So my finger has to be pushing down on it, and that makes it tip that way. It's that simple, right? So if I were to replace the ping pong ball thread with something that just held it down, then it would have exactly the same effect as just letting an iron ball dangle, right? The effect is just the buoyant force, right? Let's put it this way: it doesn't matter that it's an iron ball dangling. I could replace the thread with a rod, and then having replaced the thread with a rod on the left, I could replace the iron ball with an aluminum ball, and then I could replace it with any ball I want, because it doesn't matter what it's made of. It just matters that it's there, like the ping pong ball is. So if I support the ping pong ball from the top with a rod, that does change things, because I get rid of that thread pulling up. And if I get rid of the thread pulling up, it's balanced.
So the third option would just be have the ping pong ball just floating on the top of the water.
That's right. Let's see. So what does that do? Then what happens? That's a good one. Sorry?
I think it's the same as having it pulled down from the thread.
Well, so let me just point out this: if you have the ping pong ball dangling or just floating, and then you push it down into the water, what happens?
I think
the same as
I mean,
putting your finger.
Yeah. So I'm still walking my dogs. I have a little scale at home. I'm going to go try this. I'm guessing when you push down into the water, if you're exerting a force, then and there's pushback, then the numbers on the scale is gonna tick up. But if you release it and it just floats, then it's just gonna go up by the weight of whatever that ping pong ball, which is probably negligible. So anyway, so I'm trying to explore this. I agree with you that the left side goes down. I do not think it's because of the tension on the. I'm not convinced it's because of the tension. Like, okay, how about this? Actually, I might have this wrong. If you had a tennis, or if you had a sphere, does the buoyant force go up the as it goes down because the pressure goes up? Does the buoyant force go up, or does buoyant force the same regardless of the height or the depth?
As you push a beach ball down further and further underwater, is that what you're saying?
Yeah.
Yeah. So of course the increasing pressure will compress the beach ball.
A rigid beach ball.
Oh, rigid beach ball. Okay, if it's a rigid beach ball, then of course the only effect is the fact that the water gets a little bit denser as you go down. But if now we're back to incompressibility, right?
I don't want to get there, but okay. So it's not really the case that the deeper it is, the more buoyant force there is.
That's right,
like
except a real ball
would actually go
will
down.
will be squeezed, and therefore there'll be less buoyant force.
All right. Well, I had a whole idea about a little winch embedded in the a tiny little negligible winch embedded into the ping pong that could raise and lower the ping pong, and whether that would change the weight of the whole device on the scale, which would be ridiculous. But that's where my mind's been going. I should stop.
Ben, are you ready to? Sorry, hold on just a second, Robert. Are you ready?
No, not quite. Just give me another second. I want it to. I'm imagining myself talking through it, and it's not going to be as clear as it will be in another minute. I'm hoping. Just give me a second.
Okay, that's good. I think we got plenty of stuff.
So
to
be
be
clear,
about
I think the left side goes down because you're pushing on it from the top. I don't think the right side goes up because you're pulling on it from the bottom. I think that's. That's what I think.
Okay. I think that's fair enough too. It is the case if you look at it that way, then it's really you're looking at it as a difference between the buoyant force and the so the point is on the right. What I do is I add the weight of the ping pong ball. That should matter, and it does, right? It matters that I have more weight on the right, whereas on the left I'm pushing down with a force equal to the buoyant force. Does that sound fair?
But we know that the ping pong weighs less than the volume of water it displaces. That's why it's floating.
That's right. So the difference is that, and that's what it says on slide 13. You'll notice at the bottom there, I say the NL is greater than NR by the difference between the buoyant force, which is the force I'm pushing down on the left, and the weight of the ping pong ball, which is the force that I'm pushing down on the right. That's one way of looking at it. But when you realize that that difference is the tension in the thread, that makes it clear why you can also look at it as the only difference being that on the right, I'm pulling up with that thread.
What if you replace the ping pong ball on the right with a ping pong ball of equal weight but displaces twice the volume? Does anything change?
Okay. So now the question, right? The question is going to be a couple of questions. Are you still going to have
the tension on the string is going to double, or at least something. It's going to.
That's
increase,
right.
But does it change anything?
Now we need to be clear. Are we going to maintain the same amount of water on both sides, or are we going to maintain the level?
Oh, same amount of water. Who cares?
Same amount of
Same
water.
amount, because the level will have to change. The right one will have to increase, so that we don't change the masses.
Right. So we, so I'm not even going to offer. I'm thinking, okay, I would make a quick argument like Derek does, and if I'm lucky, it would be as compelling as Saeed's argument. But I'm not completely sure. I have to think about it a little bit more. That's a good question. It's not a very pretty question, right? Because as soon as you start like talking about making it twice as big, well, then what? I guess the question would be, how big would it, if it balanced, well, that would be very weird. Here's what I will say. If you make the ping pong ball a little bigger and it balances, then presumably if you made it bigger yet, or are we suggesting it might balance? Maybe if I make it smaller, it might balance. I don't know. There might be a volume at which it balances, but I think you can kind of see that would be something to solve for. Find how big the ping pong ball would have to be in order for it to balance if it were the same weight, but just had a bigger volume. I have to think. That's actually kind of. I'll have to think about that more.
I've been struggling because I had the wrong guess in the beginning, and I imagined two things happening. The first one is the right ball, the ping pong ball, being filled with helium, so same volume, but it being filled with helium, and I kind of imagined it kind of, if you take this to the extreme, it might even raise the whole thing up if it was the right dimensions or something. So that's kind of fixed my intuition.
Let's explore that just a moment. So filling it with helium is like on the way to a vacuum, isn't it? Because in other words, you would be replacing the air that's inside the ping pong ball with less stuff. So if you're going to put helium in there, why not just actually evacuate the ping pong ball?
Oh, we could. I'm just worried about the pressure thingy. The other thing I thought about is filling it with water. And then that, of course, will tip the balance the other way around.
That's right. Because ultimately, whether it's filled with helium or anything else, I'm just talking about, notice one of the things I'm talking about is the weight of the ping pong ball. And the weight of the ping pong ball is just that. I don't care what it's filled with. It's how much does it weigh? And the stuff inside the ping pong ball is part of, quote, the ping pong ball's weight. When I put the ping pong ball on a scale, that scale is taking into account the stuff that's inside the ping pong ball as well. If I evacuate the ping pong ball, it won't weigh as much. If I put helium in it, it won't weigh as much.
So I just came in, and I'm sure you probably covered this solution, and also you've already reviewed the answer, right? So I'm not gonna.
Yeah, no, you're free to say anything you want, Hanson.
Okay, so we probably have already covered this, but I don't know, just in case you didn't. I think there's a very direct way of looking at this, very cutting through all the intermediate whatever
Bullshit.
steps. It doesn't have to be bullshit. So the direct way of looking at this is just looking at this as a you check whether it's a closed system or not. Let's say, for example, right side. The only thing that matters is the weight of the whole system, because there's no the beak and the glass beak and the ball, whatever. It doesn't matter. There's no other force acting on it. It's just the weight, and it's not accelerating. All the things in
Ooh, don't say that word. Go ahead.
Okay.
Sorry.
So everything is static. So it's just the weight. The only thing acting on it is the weight. So it doesn't matter what's inside. Just adding up all the weights in that system, and that is just ping pong ball, thread, water, whatever, and that's the weight. And on the left-hand side, there is a outside force, or the gravity, or the iron ball, or whatever. So you only need to see is the weight, and then the water is pushing up on the iron ball, and that's what is it? You can replace it with the same volume water. So it just as if you fill up the void, occupy the iron ball by water, and voila, that's the water weight of the water, and that's it. Just the weight.
Yeah.
To compare the weight, which one is bigger? I mean, the ping pong ball, if it is a void, then it's less. It just have a void, and of course, it's going to be lighter. So that's it.
That's right. No, I think that's right, and I think that's kind of a paraphrase of what Andy was saying. I think it is true. I think I agree with you, Andy and Hanson, that the simplest way to think about this is just that on the right side I have the additional weight of the ping pong ball, and on the left side I have a downward force that the iron ball is exerting on the system. And the question, otherwise the system's the same. That downward force that the iron ball is exerting is equal to the weight of the water that it's displacing. That's effectively what Hansen said. And the downward force on the right is the weight of the ping pong ball. And because the weight of the water being displaced is greater than the weight of the ping pong ball, the iron side goes down. But it's just interesting to realize that the difference between those two weights is the tension in the thread. And so it's not wrong to say that the reason it goes down is because the thread is pulling up on the right. It's not wrong. It's a weird way to say it.
I feel much better after hearing Hanson. That was a great, the idea that it's as if you added the amount of water, of the volume displaced. So I think before that, I felt like saying that it's pushing down on the water is a little like saying you're pushing on the thread, which we agree we can't do. It sort of feels like that. Like I can't just, how does my pushing on the water push down on the bottom of but if you say it's as if you're adding that volume of water, boom, conceptually problem solved in my head.
I do like, however, I think the example, as I was talking about, that I used to do in demonstrations, just having equal containers on a scale, and then you put your finger in it and you push that side down, right? You're just pushing on the water, and you really literally are pushing down on the water, and that really is why that side goes down.
Yeah, that's it. And then in case your finger is so heavy, just like the iron ball, then you get the situation on the left.
Yeah. So let's see. What else? Who else? Anybody else on stage? No new people. Ben, any chance?
Yeah, I've still got a problem with it, which is frustrating.
So you guys, it's trickier than you think, isn't it?
Probably. But I mean, I made an algebraic error the first time and shared it, and it gave me exactly the result I wanted. But now when I've checked and fixed that, it's not as easy.
you,
So I'll
you
be,
know,
yeah, it's
I had
which
the
is
I
irritating.
had the same thing after I didn't even look at the Veritasium thing or even the I fucking love science thing until I was finished with my slides, and then I looked at it and I thought I read the link on the first page there to say that, and therefore it's balanced. And I thought, well, wait a minute. And I thought maybe I had actually, maybe my entire presentation was wrong, but I realized that they were actually talking about a second thing that Derek did, where it does balance. And I can't now remember exactly what the sequence was, but I thought, oh my God, did I make a mistake? Was my entire presentation wrong?
But
I was happy to realize it
if you
wasn't.
have a if you have a the ping pong ball, replace the ping pong ball with a gold ball,
Yeah,
and
yeah.
and yeah, they then
And then you have to have a rod, replace the thread with a rod, right?
exactly, or just
Yeah.
yeah, yeah. I mean
Stiff,
that's
stiff thing.
stiff right ball in the rod, or just let it sink to the bottom.
But notice that in that case, I mean, it's interesting to see that in that case, you still can look at it, right? The reason, I mean, it is not wrong to say that the reason it tips to the left is because that thread pulls up on the right. Whereas if you put a gold ball in place of the ping pong ball, that thread would now be pushing down on the
Yeah,
right, and that's why it would go
that's
down.
right, exactly. The and then or the dispense with the rod and let it sink to the bottom.
Right. Yeah. Okay. Well, this is fun. I don't know if
I
I'm
have
not. I
an
don't want to.
answer.
Yeah, go ahead, Benjamin. I was surprised not to hear from you yet. Go ahead.
Yeah, I apologize. I actually had to stop by at the periodic table store and get some oxygen and argon.
Are you in your basement
Um,
now conducting mad science experiments again?
Not so much. The argon is just for the TIG welder at the local makerspace, and the oxygen is for when we fly higher than about 10,000 feet.
Ah, yeah, you do want to do that.
I mean,
You
I
flying
did mad
today?
experiments in my basement. You saw that, right? Like making computers
Mm-hmm.
to implant
I
into
did.
humans.
Benjamin and I zoomed one time, and I saw his mad scientist bench.
Yeah, but I wasn't doing that today. Um, no, the answer to the question earlier is what are the weights for in the elevator controls of an airplane? It is to move the center of mass, the CG, forward um, relative to the CP, right? So that you have a more stable airfoil. And that
Yeah, I don't
probably is,
really know the mechanisms. Have to take a look at them. I don't
well,
really understand that. Is it just basically
wait,
hinged
CG?
with so it's just a hinged thing, right?
Okay. So let's imagine, for sake of argument, that you build an airplane and you put a an airfoil in the back and you hinge it right down the middle line so that an equal amount of it is forward of the hinge and an equal amount is behind the hinge.
Uh-huh.
And then when you're in the air and you rotate that hinge around, it's hard to say whether it would want to be in any particular direction because in all directions it has an equal amount of force on both sides of the wing form.
But there is
So,
airflow trying to kind of straighten it out, right?
well, what does straighten it out mean if you're tied to the middle? The honest truth is that wing airfoils that are held by the middle tend to rotate. They spin. They make like spinning kites out of this model, right? But if you didn't allow it to spin and you just controlled it a little bit, it would be really easy to control. It would be so easy to control that it would probably be scary. I'm quite sure it would be scary. So then you could move the axis forward even like 1 inch and it would have a tendency to straighten out, but just barely. And then you could move it till the axis is all the way on the front, and then it has the maximal amount of desire to run straight. And that
I think
turns out is like really hard to use.
So I think I still don't really understand. I mean, I wish could just see a diagram. I'm looking at the Wikipedia page on elevator, and it just shows me kind of what I think of as a flap that hydraulically lift up to make the nose go up, or lift down to make the nose go down, right? Just with airflow across the elevator. But I don't, Andy was talking about stabilizing it by just giving the elevator more inertia, so that when it's in its normal, just kind of level flight position, it doesn't start fluttering somehow. But I don't think I really understand quite where this mass is that you're talking about.
Can I
The mass
interject
that's added
what
is
and then
always added at the leading edge, and it's
At the
often
leading
like an
edge.
artificial.
Yeah.
Yeah, nobody
In
adds
front
mass
of
at
the leading
the
edge.
trailing edge. Yeah,
Well,
you
yeah, what
could
does
say it's
leading
in
edge
front of the
mean?
leading
Yeah.
edge.
In front
Well,
of the lead.
whatever
But
the
that's the
edge is
hinge, right? Isn't the
that's
leading
from.
edge the hinge?
In most cases, we could say it's the hinge. If it's an elevator, then the leading edge is a hinge. And if the hinge is at a point that's not where at the leading edge, then we call it a stabulator, I think. And that
Huh.
can mean that the entire rear fin moves.
Hey, before we
But
go too far down
most
this
of
road,
them,
hey Benjamin, can I just say this is a great
sure.
this is a great subject, completely different than the subject of the room. But before we go to this, I just posted my Python code in a collab document in the chat. I especially want Hanson and Ben and Benjamin to take a look at Inshamash. Actually, anybody can look at that. Free to look at it. It's in a collab. You can't run it. You can't run the code in the collab because it uses the Pygame library. So it's got to be. I'm running it on a PC. It should work on a Mac. I haven't tried it on a Mac. So it's going to run on a computer, and you have to have So you have to basically paste it, copy and paste it into a text file, and run it locally from a Python interpreter. So if you know how to do that stuff, this is pretty easy to do. And you might have to install Pygame in order to, because the script wants Pygame installed.
So Andy,
yeah,
I've just
I might have to
copied
go, but
I've just copied and pasted that into a text file, which I would then, if I would get my Python running, I would just take that text file and label it blah 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 apollo.py, and then just open that and run it, right?
yeah, then you just from the command line you type Python space apollo.py. But it sounds like you installed a newer version of Python, but it still opens up the old version, so you got to reset some environment variables or something like that.
Yeah.
Or you can go into like the new installation of Python might have an editor like idle. I think it is what comes with it. Depends on which distribution, but it usually comes with its own console, and in that console there's usually like an open file, like run file, and you can just like run, point to that file and run it that way. And that way, even if in the environment it's pointing to the old version of Python, you can still force it into the new version of Python.
What is this code for?
It does the lunar thing. It's a code that Andy and Gemini wrote in a collaboration to to simulate spacecraft, orbiting the moon or orbiting the Earth and the Moon system, and then you can give it an arbitrary initial place and velocity, and just watch it go to the moon or do whatever you want.
If you can get it to run,
moon,
it's completely self-explanatory, but it might be challenging to get it to run.
Yeah.
So you've already tested it, or
he's been running it, yeah, and making it better, adding controls and zooming in and slowing down when you zoom in.
Actually, the little
all sorts of
red
fun things.
trajectory on my PTR is the spacecraft orbiting kind of in the vicinity of the moon, and then actually kind of chaotically getting trapped back in the Earth orbit for a few minutes, and then getting recaptured by the moon. So it actually captures some chaotic dynamic behavior, which is awesome.
cool.
Yeah, it's very cool.
And so just want to ask, what was Benjamin talking about earlier?
Well, he's talking about elevators on as in plane elevators, the things on the tail that you use to control pitch.
So there's an interesting accident. A guy named Rob Holland dies.
Oh, actually, can I just we'll come back to this interesting thing. So just here's a variation on the John's theme of the buoyancy. And what if you, okay, so instead of the ping pong ball, make it into a kind of a rocket, streamlined, pointing upward. The kind of the I don't know, yeah, rocket maybe, or submarine shaped, pointing upward. So the viscosity and ignore all the viscosity, the water and all the friction and all that. What if you cut the thread, and at the moment, especially at the moment when you cut it, what is the scale? Is it going to be tipping, or is it going to be level?
Oh, that's right, because the center of mass on the right will be moving as a result, right?
Yeah, but let's say at the right at the moment it's cut, and ignore all the viscosity, friction, moving friction, and all that. And what's the scale? What's going to be? What is the scale would look like?
Right, right. Because I think you would still have, if you've got the ball moving, the ping pong ball moving up, then what's happening? You've got the viscous forces that, of course, it's all part of the system still. But I think the problem, the probably ought to be answerable just in terms of the fact that the center of mass of the object on the right is now descending, right? And that descending center of mass, well, I'll have to work out what that means, but I think it's all in terms of the fact that the center of mass is descending. Doesn't matter. The viscous forces don't matter. Those are all internal.
No friction. No, let's ignore all the friction.
Well, it doesn't even matter. They're all internal, right? But ultimately, it's because as the ping pong ball rises, the center of mass of the thing on the right is going down. So that's going to have an effect that requires some force itself. I have to think about what that means, but yeah, no, that's it. Well, okay, so that's right. Another good extension. Now we've got
so here's
hydrodynamics.
Here's the mass and the counter rotation of a wing, and I wanted.
When you say
John,
here, what do you mean?
Can you formulate the question?
Yeah, I will.
I will clearly.
Here, very clearly,
succinctly. Yes.
So Rob Holland died in a custom-built aerodynamic airplane because one of the cap screws that holds the wing weight came loose during flight, and the reason he had a cap screw on the elevator weight was so that he could change the elevator weight depending on the kind of flying.
For anyone, including me, who's not familiar with the aeroplane jargons, what is elevator? What is all the put it in
so an airplane is a thing that goes in the air.
Simple idealized model.
It looks like Superman. It looks a little like a bird.
So you can look at the Wikipedia page to understand an elevator if you don't, but I still don't. So this cap screw is holding the weight to the elevator near the hinge. Is that right?
Well, it's more like the cap screw just is like the pill bottle cap of a section of the airplane that's empty, and you can put whatever you want inside the pill bottle and then screw the cap back on. So he's got this hole where the weight goes, and he's got this cap that covers it so he can adjust the weight. Now, I mean, he died because his airplane failed because he had this cap control. It was very important to him to be able to control the weight of the elevator, the weighted portion of the elevator, in order that he could
controlling it in the sense that to change it before a flight for some reason.
He could change it before a flight, right?
Yeah,
he could change it before a flight. And that was important enough that he deviated from the airplane's tested design, and he died. So I got to thinking, like, why is this weight so goddamn important? And I thought you could explain the physics of putting a weight in that position of an elevator. Now, to Andy's point, this position is sort of artificially in front of the wings. There's a portion of an elevator, very often, most control surfaces actually, which is sort of artificially in front of the hinge. That is to say, they have an extra arm that they add in that creates some like control in front of the hinge.
But that part is fully embedded in the stabilizer, right? It's not subject to aerodynamic forces. Am I?
Well,
I feel like I'm not under, because the elevator is something that fundamentally is just hinged to the back of the stabilizer, right?
Yeah, that's exactly right. And then there's this forward control arm that
which is inside the stabilizer, because otherwise it's going to stick out and grab air in a really bad way, right? You need that part to be shielded from the aerodynamics,
or in a really good way.
Or in a very good way.
Yeah, Brian knows something about flying too. So,
well, the picture I'm seeing here is we're talking about trim tabs that would be on the trailing edge of the elevator, that is the moving part of the elevator, and then sometimes some planes have a little tiny part that extends forward, and that provides when you actuate the elevator, then there's a dynamic force on it from its lift that causes it that goes against the pilot's desire to hold it in position, and this little thing that sticks forward provides a little aerodynamic force.
A little aerodynamic push.
A little bit, and and unloads the elevator that's providing the pitch control, such that the pilot doesn't have to exert so much force on it.
Okay, that makes sense.
Right.
But it also increases the drag, right?
Slightly, because it's a small piece.
Yeah.
There are also
I don't know that it increases the drag. I would say
it would have to, wouldn't it?
Of course, anything that produces lift is going to produce some drag.
Yes.
Yeah, and this is producing drag in a weird way, right? It's for a good purpose, but it's kind of a weird thing because it's capturing air on the opposite side of the elevator that you want to be.
Not really. No? So, little diversion. There are dropouts on our airplane on the ailerons, which is like a very similar control surface on the main wings.
At the outside of the main wings, right?
Yeah, outside of the main wings, which are counter-connected, meaning when the left goes up, the right goes down. It's not the case with the elevator. With the elevator, the left goes up, the right also goes up, so they're connected.
Right.
The ailerons are cross-connected. Now, in our airplane, there is a dropout, which does exist for the sole purpose of creating drag, which is meant to counteract adverse yaw. But that's not what I asked you about.
Right.
And
Otherwise,
Brian
you have to
is
do that
right.
with the rudder.
Yeah, the portion on the front of the elevator is, you could think of it as extra. However, it's not really extra, because it can be as big as 75% of the wing surface can move, and it would still be an elevator. But you get to the point where 95% of the wing surface is moving, you just give it another name and you call it a stabilator, which means you've combined now the stabilizing airfoil and the controlling airfoil into a single surface called a stabilizer.
Oh, right.
But otherwise, you have what's called the stabilizer, which is the stable part of the back. It stabilizes the airplane up and down. And then you have the elevator that manipulates that. So you have some stability and some control. And this is what it is, a blend of stability control. If you have too much stabilization, you can't do aerodynamics, right? You might have something that's nice as a commercial airplane to move passengers, but you're certainly not going to do a hammerhead stall. So if you have maximal control, then you have something that can do amazing aerobatics, but will tire a pilot out immediately. They can't fly it for more than 30 minutes because there's so much work involved in just keeping the airplane stable. So that's the balance between stability and control. Now, getting to our weight. Yes, any airfoil in front unburdens the pilot from the force of controlling the aileron, the elevator. All airplanes have something along these lines, as far as I know, except for maybe a couple small airplanes. But the question is the weight. Why the weight? Why did he care so much about the weight? I have to inspect the weight every time I walk around the airplane. I'll put my finger on that part and check to make sure it's there. But this got me thinking, why was it so important that it was there and that he could change it, that he was willing to modify the airplane and kill himself? The best answer I have is that weight moves the CG of the entire airfoil forward. And there is this principle in rocketry that the airfoil will naturally rotate around its center of gravity, center of mass rather. And if the center of pressure is behind the center of mass, it is what we call a stable rocket. And if the center of pressure is in front of the center of mass, then we have a rocket flying in reverse, which is often soon straightened out naturally.
Well, I rather liked, what Andy was saying. Maybe he wants to weigh in here, but it strikes me that there is going to be this potential with an airflow kind of a thing, vortex shedding and all, that you could set the thing into some kind of an oscillation, and that the inertia might have something to do with that. But other than that, I don't know.
I agree with John. I'd like to see the configuration of the system, and it sounds interesting. I'd like to see how it works.
Yeah, there's a lot of configuration. Just about any configuration you can imagine has probably been tried. But it's not just to balance the weight, like gravity-wise. Like even a vertical rudder will often have mass on it too, for the same reason. It's like a tuned mass dampener that they put on, structures like skyscrapers and stuff. It doesn't totally surprise me that somebody might want to have an adjustable one, although that's the kind of thing that like the designer does. The pilots don't do that. And so it's an odd thing, but that was an experimental aircraft. It was in the experimental category. So the dude was experimenting. Here's a little fun trivia. The Bell X-1, which was the rocket plane that Chuck Yeager flew and first broke the sound barrier. One of the things they realized was that the hinge in the elevator to stab was the place where when the shockwave got there, it would cause all this flutter and rip itself apart, and that's why a lot of airplanes got killed. I don't know if it was the first time that a stabulator is basically like the whole thing moves, the entire surface moves. It's how most like commercial planes are nowadays. So the whole thing moves, and what they did to hide, they actually painted a line along where the hinge would be, and they also put a fake propeller in front of it just to I don't know, throw off any would buys. I just thought that was as relevant as the rest of the conversation. So.
By the way, my PTR is a sketch of the apparatus that I found on some website. Pretty much what I was thinking, but it kind of shows that little nub sticking up on the opposite side of the business side of the elevator, and I can see. It doesn't look like it would provide much help to the pilot, but you do get a little drag there, a little push to help kind of keep it in that item. Anyway, I don't know if that's an accurate.
You might be looking at the trim tab, which is it looks like a tiny little control surface, which is completely meant for a different reason, which was to balance. It's to balance the forces. But for this Rob Holland crash, one of the notes they made was that the trim tab was in the full up position, which meant that he had trimmed the nose down all the way. So something was up with the balance of the plane. And it takes a while to do that, so he must have got himself into that condition early on, well before the crash, I think.
It seems like this site has some pretty good information. I'll put it in the link and in the chat. But that's supposedly a drawing of the elevator and stabilizer, and it talks a little bit about other designs. So maybe that's useful. Anyway,
John, when you're ready, I have got what I think is a good solution to this now.
Yeah, let's
Finally.
let's abandon this for a moment. Go back to the topic of today and let Ben give his spiel.
So have
Go
a
ahead, Ben.
look at it, John. So in the chat, it's just in almost immediately, just a few seconds ago.
Yeah. Okay. Let's see.
So I'll let you look through it before I say anything, because you can probably do it very quickly.
Well, just a bit before that, just want to add, John, my variation, the viscosity and the friction matters.
Hold on, Hanson, one second, because I don't think you can both follow your argument.
Yeah, let's
that at the same time.
Yeah, no, I think this is what we were saying probably while you were working on it. So yeah, it's right, as far as I can tell. So go ahead and give your take on it. I think
so the way
it's maybe a slightly different way of saying the same thing.
Yeah, I think it probably is a slightly different. So what I said, I think in the very beginning was just looking at it. My brain draws the red dotted line in my diagram around the system. It's slightly non-rigorous why, but that's what I'm seeing as. It doesn't even matter because I don't use it in the analysis. But I'm saying on the right, you've got the weight of the water plus the weight of the ping pong ball, which is important. There is the ping pong ball has a weight, and on the left, pushing down, you've got the weight of the water plus what must be a reaction force to the buoyancy from the iron ball onto the water, because the water must be pushing up on the iron ball, so the iron ball must be pushing equally and opposite down on the water. So I think that's what you've got left and right. Yep. So it's pretty simple after that. You just take torques around the pivot. You don't even need to worry about the torques. Who's doing the... That's you, is it, John?
That's me. I'm going to go on mute here for a second, but go ahead.
So you don't even have to bother with torques because we're assuming, and it doesn't say in the question, we're assuming that both of these arms are the same length. It probably says that in the question. So you're really just looking at the forces on the two sides. So that's it. It's in the diagram. It's pretty simple. It will tilt left as long as the ping pong ball is lighter than the water, which it is because it floats. It's just kind of as simple as that. So as long as the ping pong ball is positively buoyant, then it will tilt left. And it seems odd to say it like that because on the surface it seems to have nothing to do with the weight of the ping pong ball, but it does. So anyway, that's it really. And my solution's in the chat, and it's, I think, fairly simple, single page. What I was working on, John, is trying to get it down to a single page. Because otherwise I was waffling on for ages. So.
And if there's any doubt, in my PTR, I just suspended a lemon in some water and did indeed see an increase on the weight on the scale that it's on. So in case there's any doubters. It's actually a lime. These are yellow limes. We bought a yellow lime tree, and it's right next to our lemon tree, and then I immediately was like, what a dumb idea. Now I can't tell my limes from my lemons. But they're delicious.
We have the same thing. We've got exactly the same thing. It's Bear's limes, right? Are they Bear's limes?
I don't know what they are, actually, but I just know them as yellow limes. But my neighbors love them.
Yeah, they're great limes, and they are yellow,
scurvy.
and we have a lemon tree right next to our lime tree. The only difference is the lemons are bigger.
Yeah. We have no scurvy in our neighborhood because we provide all the citrus necessary.
Yeah. Sorry, I missed anything fun there. I had to. My wife is away from the house, and her battery's dying. I have to deliver a battery to her pretty soon, so I'm gonna have to shut this place down.
Well, I did confirm that a partially submerged lime will increase the weight on this. So I had my doubts. I wasn't totally sure.
Yeah, but Ben, your diagram does say the same thing. Ultimately, it is as I was kind of saying it two ways. You can show rigorously, as I did, that the difference really can be looked at as just the fact that on the right you have the additional weight of the ping pong ball, and on the left you have the additional push down, the reaction force to the buoyant force, and because the buoyant force is bigger than the weight of the ping pong ball, the left side goes down.
But
it turns out.
Sorry, go ahead.
Sorry, and then it turns out that because the tension is just the difference between the buoyant force and the weight of the ping pong ball, it is completely legitimate to view the difference as simply being that on the right you have a thread pulling up. That the amount that it pulls up is exactly the difference between the two forces on the left and right. So it's completely legitimate to view it that way.
But that's only because the two balls have the same volume, right?
Sorry?
That's only because the two balls have the same volume.
That's right. Only because they are the same volume.
That's
Yep.
messed up.
Yep. Well, I shouldn't say that exactly, I guess, because, and maybe that's the point, is if I made the ping pong balls, if I made the iron ball smaller, right, I could decrease its displaced liquid to have the same weight as the ping pong ball. And I guess at that point, if I made the iron ball small, just the right size, I could make them balance.
Actually, it doesn't matter. The ping pong ball can be any size, so long as it's not zero. It's always going to be lighter. Just think of
right.
The
ping pong ball can be any size, but if you want it to balance, you'll have to make the iron ball
right. If you
smaller.
If you want the statement to be true that the force down on the left is exactly equal to the tension, then they have to be the same size. So my point is that's kind of sort of irrelevant, even though it's true.
Actually, it doesn't matter. Like I said, I mean
that's true. I like that, Andy.
Yeah. So long as there's a ping pong ball, however size, whatever the size is, it's also going to be lighter. The bigger the ping pong ball is, the lighter it will be. So long as it shrinks to zero, it's going to be lighter. And then also, when you're thinking about the thread, right? I mean, I have to promote my variation. It's has a very simple answer to it.
So I think the thing is that you say it's always going to be lighter. Yes, it's always going to be lighter as long as the iron ball is, it does depend, right? I mean, the fact is you could make the iron ball smaller.
Yeah.
And then it wouldn't be lighter.
No, smaller, the weight is going to be the same.
It's the weight of the displaced fluid that matters, and you could make that be the same as the weight of the ping pong ball.
Yeah, well, the thing is the iron ball, it doesn't really matter because the whole thing is you could just replace whatever in that space with water.
Right.
It doesn't matter what the shape is, what the size is.
Right.
You just replace it with water. That's it.
That's right. And so if you make the amount of water that you're displacing equal to the weight of the ping pong ball, then they balance.
Yeah, because the thing is, the left.
Yeah, that's
side
what the last line on my solution exactly says.
Yeah,
it says it'll tilt if the weight of the ping pong ball is more than the weight of the water. The break-even point is when the density of the ping is that of water.
Yeah, exactly. So
and it's kind of weird that it makes any difference, by the way.
No, it's not quite that, right? The break-even point is when the displaced fluid on the left is equal to the weight of the ping pong ball on the right.
But holding the ping pong ball's volume constant, that's the same thing.
Right. So okay. So
which you did in the question.
It's still the same principle as I said earlier, right? On the right, you just count all the weights. That's it. Nothing more. And then on the left, it's just water. That's it. There's no ball whatsoever.
Right.
It's just water. Yeah, that's it.
That's right. And if that water weighs the same as the ping pong ball, then they balance.
Exactly. You can put in whatever you want, gold, silver, whatever, and just count all the weights on the right, and it doesn't matter. And then
So when I first looked at this, John, I what I said didn't take into account the possibilities of the weight of the ping pong ball at all, effectively. I kind of intuitively knew it would not matter, but I wanted to do it. I wanted to make sure that it was in the solution, and then it effectively cancelled out because the ping pong ball. The only condition is that the weight of the ping pong ball is less than the weight of the water it displaces, which it is because it floats, which is in the question. Which is
Well,
quite
but the only
interesting.
reason the thing that matters is how much weight it displaces.
It's because it's
is
the same
because
volume
that's
as
the
the other
same
ones. Yeah,
as the
exactly.
iron. Yeah.
Yeah,
Right.
exactly. It's quite funny, isn't it, to reason about? It's a good question.
Yeah. Yeah.
Yeah. So should I review the answer to my variation, or
Go ahead.
wait for later?
Go ahead. But then we're gonna move pretty quickly toward closing because I have to go rescue my wife.
Okay, cool. So if you cut the thread on the right, at the moment you cut it, the two sides should balance. The weight should level. There's no tipping whatsoever.
Let's see. Do I can imagine that? I'd have to think about it some more. I think that's a good variation.
Wait, if you cut the thread on the right, it balances?
Yes.
I don't believe that.
Think about that.
Well, I like it from this standpoint because it is, if you think of it in terms of, like I did, that the only difference is the tension pulling up,
then
that kind of makes sense.
Well, if you look at my solution, what happens when you immediately that you cut the string on the right is that the weight of the ping pong ball at that moment disappears effectively. It has no contribution until it starts moving upwards and has a viscous drag that gets to its terminal velocity or whatever. At the moment you cut it, it ceases to contribute weight to the system, I think, and therefore the only condition is that
so the thing is, the weight, the thread, the effect of the thread earlier before it's snipped was basically canceling the force upward and downward out. And then the buoyant force, it's pulling down and then also pulling up on the bottom, so they cancel out. But when you cut it, after you cut it, the buoyant force is still there, but the pulling up force by the thread is disappeared. So
see, here's the part that I still think is hydrodynamically, when that ping pong ball starts to move up, it's pushing up harder on the fluid above it now than it was before.
Just as you cut it, before it picks up any speed.
I told you, that's why I said at the moment you snip
the moment you cut it, exactly. At the
Well,
moment.
I think that at the moment you cut it, it begins pushing harder on the fluid on the top.
That's why also I said viscosity. Don't count the viscosity and the friction. That's why I said that.
Yeah, I think that's getting a little hard for me to. I think in this case, that's a little hard to involve.
The thing is, discount the viscosity and the friction. That's when you start gaining velocity. And then,
I don't even think we need viscosity or friction. This is just hydrodynamic. This is just ram pressure.
Right.
This is just
okay. But the thing is,
1/2 rho v squared stuff.
At the moment, time zero or time epsilon, when you cut it, there's no.
Oh, and there's no v. You're right.
There's no v. Exactly. Effectively,
no v.
Effectively,
that's
the ping
right.
pong ball contributes no weight for that in the very
that's
first instance.
True.
So if you look at my final equation, which says that it'll rotate provided that the reaction force is greater than the weight of the ping pong ball. So if you take away the weight of the ping pong ball, then it will. Then you're taking away for just a fraction, for an instantaneous amount of time, you're taking away the weight of the ping pong ball from the system.
Let's hear what Legend has to say. Welcome, Legend.
Question. So when you cut the string, and this is just question, when you cut the string, does it not push off of the water, like actually give you a force?
That's what I was saying too, and I think Hansen is right now. If it's a non-viscous, no friction kind of a thing, then the only way it can affect that is if it exerts a ram force, which depends on velocity. It has to be moving to exert that kind of a force. And at least immediately after you cut the string, it's not moving, so it can't exert that kind of a force. Is that fair, Hansen?
Yep, that's it.
Yeah.
So I guess I misinterpreted what Hansen said, how he set that up. I was sort of thinking it in terms of like the stable state after you cut it, after however many seconds the wobbling stops. And in that case, I think we would all agree that it would be back to the original state. With the ping pong ball floating on top?
I
mean,
think
stable.
so.
No, I mean, if it is stable, meaning
Yeah,
if
once
I
it's stable and
understand,
floating, you're back to tilting
understand,
left.
yeah. If I understand it is stable, meaning no acceleration, then it's still going to be lighter. The right side,
Right,
it's going to be the
right.
same as
Terminal velocity
same as
or floating.
yes.
Yeah, again,
Terminal velocity upward or floating, either way, right?
yeah,
Yeah,
exactly.
same thing.
Oh, you
And
introduced acceleration, I have to say.
Unfortunately, it is about acceleration, I have to confess. Yeah. Okay, well that's cool, and maybe just to bring it around full circle, point out that it doesn't matter what G is for this thing, right? It just matters that there be a G. So you could do this in a upward accelerating elevator, et cetera. What you can't do is you can't do this in the space station or in a falling elevator or whatever.
The only thing the G matters is how much rotation, how fast it's going to
How quickly, yeah.
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 But I have another variation, a more ridiculous one. Back to my idea with the negligible weighted tiny little winch. Instead, make it a tiny little pump that can inflate this thing to twice its volume and deflate it. Don't ask how it works. It just does. It's like a swim bladder in a fish. In that case, when you inflate it, you'd be increasing the tension. So do you think you can get this thing to rock back and forth by?
Well, so I think the problem with all these analyses is that built into the analysis that we've done here is the fact that the buoyant force on both sides is the same, and as soon as you violate that, then you're trying to somehow keep that for part of the problem at the same time that you're trying to get rid of it for the other part of the problem. So you really have to redo it, understanding that now there's two different buoyant forces.
Yeah. So the thing is, I mean, if it is the ping pong ball, if you inflate or expand like the fish and all that, it really doesn't matter. So long as you do it, with respect to the center of the ball, so no
Yeah.
acceleration again. Yeah. And then
That's right. And I think that really does argue against, as Andy said a little while ago, my explanation in terms of the tension. The explanation in terms of the tension only works when the two things have the same size.
Yeah, but on the other hand, if we put it on the left, and then if it's an iron ball, or whatever, it doesn't matter, iron ball, and then you oscillate that, then the scale will oscillate.
Or the glass would break and the water would rush out and the right side would go down.
The thing is,
Okay,
so you don't get just, and then I know you want to finish, John. Is what you say.
Yeah,
As soon as somebody changes something, you need to go back and revisit your assumptions. But if you get it down to the like 7 or 8 lines that I've got there, it's not very difficult to go back and redo that. You say, hey, what about if? And you go, well, my line 2 would be wrong, so let's redo it. This is why it's really important to do things in as compact a way as possible, is because of iteration.
That's right.
Not just so you can iterate faster and deal with the what ifs a lot more capably if your solution is as simple as possible. It doesn't mean that when someone comes along with a curveball, it won't suddenly get massively more complex. That could happen, but at least you can very quickly say, yeah, this is still valid because your assumptions are so brief.
Yeah, that's true. I mean, that's why you want to cut to all the crafts and then just the essence.
That's right, and I think really the general way to say it is just what Andy and Hansen and everybody else said. Don't think of it in terms of tension. It really is, the difference really is how much heavier is it on the right, and how hard are you pushing down on it via sticking your finger in the water or dangling a heavy thing in it. On the right, you're pushing down with a force equal to the displaced fluid. On the left, and on the right, you're pushing down with a force equal to the weight of the ping pong ball, and nothing else matters. Doesn't matter how big the ping pong ball is. Nothing else matters, right? Other than the fact that the same container, same water, all that stuff. Yeah. Okay, so I think we've solved that. We haven't quite solved the elevator problem, but maybe we can return to that. I really do have to go. So, Brian, did you see you unmuted? Did you want to say a few words?
I just wanted to point out that, except that it also has a transverse velocity to space. station is also a falling elevator.
Right, right. Exactly. And that's really an important point. I mean, that's really the way I really want us to understand that G in the way I want us to understand the gravitational field strength is that it is reference frame dependent. And in the International Space Station, there is no gravitational field strength, despite the fact that it's just a couple hundred miles away from us.
One other final irony, and that is that on that note, we used to call G the gravitational constant, right?
Well, that's a different G, right? I think you're thinking of big G.
Well, okay, maybe. I may have also used it for little g myself, and maybe erroneously.
Usually, it's
if you
also
go far
called
enough,
universal gravitational constant.
I think
Go
if
ahead,
you go
Ben.
far enough back before we understood universal gravitation, I think people would have considered G to be a constant. Everything accelerates on Earth.
That's true.
At a constant rate. You know, the feather hammer.
Especially
trick.
when the Earth was flat.
Yeah. Thank you for saving me. That was the era of which I spoke. Maybe a little bit older than John's era, at least by a year.
Hey, John, I'll spin. Lots of people want to talk. I'll spin up a quick follow-up room now.
Okay, that's great. That'll be great.
It won't be long, but just while I finish the dish.
I'm gonna join it myself, but I'll be in my car and. Yeah. Okay. All right. Good. So we'll see you all next time. And wait a minute. I have a quick announcement to make. There won't be a next time. The next couple of weeks, I'll probably have to talk to Ben. Maybe he'll want to do a substitute room. But I am going to be cruising to Alaska for the next couple of weeks, so I won't be doing the bite of physics. Yeah. So maybe I'll check in, depending on my internet. Maybe I'll check in, especially if I've got Ben or who knows. Maybe we'll even get Andy to do his whatchamacallit thing. Scan. Maybe, anyway, whatever. Anyway, we'll look for some kind of a substitute. But I won't be hosting this next week. Maybe somebody else will. And until then, we will
That sounds
see
good.
you.